I'm sure that you heard the cars as you were led up the lift hill. Do you know that noise I'm talking about? That clicketing and clacketing as it goes up to the top? How many of you don't like that noise? Okay. Do you not like it because you think it's scary or just loud? So one of the things to consider is that you want to hear that noise. Right? What you're hearing is the safety system. It's a small ratcheting system that has basically a piece of metal and a gear. And the gear is actually built into the track, and the piece of metal sits on the car, and it's banging on the gears as it goes up the track, so that if the chain breaks, when the cars start to roll backwards, that piece of metal wedges into the gears and stops the car from rolling backwards. You want to hear that. That's the safety system. They let it bang around because they think it makes you freak out. That's on purpose. Now, has anybody ridden, let me see, what is it called? Expedition Everest? Yes. Okay, so that uses a chain lift too. It uses one of the fastest chain lifts in the state. What's interesting about that chain lift is that you don't hear that clicketing and clacketing. And that's on purpose. The chain lift there, they want it to appear like it's a real train. So to do so, they use magnetic induction to lift the little bar up so that it doesn't hit the track. So it's like the train is pushing you. But the moment the wheels stop, the metal falls back down. Yes, go ahead, Gabby.
That ride goes backwards for part of the ride.
Yeah. So all of our roller coasters have that. Now, interestingly enough, that's to protect the cars from going backwards into the loading house. There are rides that fail at that. The Hulk was famous for failing to launch and the vehicle going back into the loading house. They had to develop a place to hold the other car, the other train that they'd be loading back a ways, so that if Hulk failed to launch, there was room for the cars to come backwards. And they had an emergency system in place for that too, because it didn't use a traditional chain lift. Now, traditional chain lift, this section of the ride is not conserving mechanical energy. This section of the ride is where the chain lift is. The chain lift has a large chain that exists between two wheels, one at the bottom and one at the top. And that chain has a little thing on the back of it that will push the cars up the track. It just physically pushes them up there. It does physical work. And as we talked about yesterday, whether we go up this incline to get to the top or we cobra curse it straight up to the top using an elevator, the same amount of work is done. And that's because gravitational potential energy is path independent. Again, gravitational potential energy is path independent. It doesn't matter what path you take to get to your height. All that matters is what the change in height ultimately is. So whether I go this slanted way to get to the top, or I go straight up to get to the top, the same amount of potential energy is gained by the cars. And we're talking about mechanical forms of energy. So if we exclude things like friction, bless you, and air resistance and other non-conservative forms of energy, once you have put energy into the system, the total energy of the system should remain constant. Bless you. That's the last one. I'll say it again. Once you put energy into the system, the total amount of mechanical energy should remain constant. Right now, you only have two forms of mechanical energy that we've talked about. Gravitational potential energy is a form of mechanical energy. It's about height. The other form of mechanical energy is kinetic energy. It's about velocity. So again, once you put energy into the system, the total amount of mechanical energy will remain the same. I said it 3 times, right? That's enough, right? Do we all have it written down nice? So. Now, I want to be very clear here. I keep using the word system. Do you know what the parts of a system are in this case? Because you're going to be asked this question on the test. The roller coaster vehicle isn't the system. Because the roller coaster vehicle doesn't have any gravitational potential energy without interacting with something else. What must it be interacting with that gives it gravitational potential energy? It's a big thing. We're all standing on it most of the time. Yeah. When we talk about system, the energy in this system is between the roller coaster car and the Earth, because gravity is involved. So when we talk about potential energies are always two or more things interacting. There has to be an interaction. So our system is the Earth car system, and the energy is stored in that system. The track is in the way, but it's not really part of the system. When we start including friction in this, then the track will be part of the system. But right now, if we're ignoring friction, the track isn't really part of the system. Now, what this ultimately means is that if you add these two forms of energy together, the total energy is always going to be the same value. But it's going to be broken up into different kinds of energy at any one time. For example, at the very top, I think we can all agree that the cars are above the ground, so there's definitely some gravitational potential energy. But also at the very top, usually the cars are barely moving. That's important. We want you to think about your life choices that led you up to the top of this hill. They want you to be scared. They want it to be nice and high. And they want you to look around a little bit and be nervous about how high you are. So often, they're usually moving very slow, or in the case of like SheiKra, they're stopped. But at any point in this ride, there's the possibility that the cars have gravitational potential energy and or kinetic energy. But I can say this, if you reach a point in the ride that is lower than where you were lifted to, it should be clear that you will have less gravitational potential energy there, because MGH is a smaller number. But since the total energy has to be the same, if it's not in the form of potential energy, it sure better be in the form of kinetic. So as the cars make their way around the track, the cars are always exchanging potential and kinetic energy. So assuming we're talking about, say, something as simple as Scorpion, which was not even open, if the lift hill were 60 meters high and the radius of the loop was 15 meters, let's figure out how fast the cars were going at the top of the loop. Let's say the cars are 100 kilograms with passenger. As students, please notice that I'm drawing just one car, not a whole train of cars. If you want to really get into this and go into designing rides like this, there's a big difference between one car and a whole train of cars, because the train of cars, you have to monitor where the center of mass of the cars go. And the center of mass of the cars is never at the maximum height, because it'd be an entire train of cars. So the center of mass will be lower than this. So real roller coasters behave differently. So I'm purposely just drawing one car, and assuming our roller coaster is just one car, more akin to SheiKra, which is very small in length. That's more like what this is. Real roller coasters behave different because the center of mass of the cars is what you have to monitor. That makes them more complicated. Now, a conservation of energy problem is actually stupid simple. There's only 3 possible energies at any point here, and you can have one of them or all of them or none of them. So when you look at this, it's likely you are going to have at least one form of energy at each place. For example, at the very top of the hill, what form of energy are we likely to have? Potential. Yeah, gravitational potential at the very top of the hill. At the top of the loop, what form of energy are we very likely to have? We're probably going to have kinetic. I would assume we do, because we're not as high as we were before, so although we'll have gravitational potential, there will be less of it. Does that make sense? And the sum still has to equal the total amount of energy in the system. So these have to be equal. That's quite literally all you have to do for a conservation of energy problem. Set the energy at one state equal to the energy at the other state. Now, I gave you the value for the mass of the cars, and I gave you the height of the hill and the radius of the other hill. You should be able to work out the velocity. That's an arithmetic question. And I'll do this for you once. But after this, it's really small potatoes, and I expect you guys to be able to do this. Maybe jot some notes on the side for what we're about to do here. But how high are we at the top of the lift hill? 60 meters. And how high are we at the top of the loop?
30 meters.
30 meters. That's right. So those of you who said 15, again, not paying super close attention, the radius is 15. But from the bottom to the top here, it's a diameter. Right? Don't be fooled by something as simple as that. So, top of the first hill, mg h minus h naught 60 equals, at the top of the loop, mg h minus h naught is 30 plus 1/2 mv squared. Okay, nothing new there, but mgh is new from yesterday. Now, I did give you the mass of the cars, but are you noticing something about having the mass of the cars? They're going to cancel out, and that's going to happen a lot in these. As maybe a small aside in your notes, if you're asked for how much energy there is, you will need the mass. But if you're not asked for how much energy there is, but you're asked for some facet of the car's motion, you probably won't need the mass. It will probably cancel out. You guys all hear that? So if the problem didn't give you a mass to work with, put an m in there, but be aware it probably will cancel out. And in here, the mass does cancel out. We all good over here? Ask your question now before we get 10 minutes from here, and then I get all cranky. Don't start with an form the words, put them all together. They're equal. Well, the easiest way to explain that is to say, I said so. And that should be enough. But I'll repeat these words. If there's no non-conservative force acting in the system to change the energy of the system will not change. Did you hear that?
It's because it's the same energy no matter what.
The total energy will stay the same.
So from the start to the end, it's just the same, so they can be.
Yes, we've said it 4 times now.
Yeah, I wrote it down. I just.
Okay. That's why I made them equal, because they are the same.
Okay.
I'm not trying to be facetious. That's why. Nothing took the energy away. Now, I'm going to try and trick you shortly, so I want to make sure that you understand. I'm making them equal here because I believe there's no force acting on the system that would remove energy from the system. So the total amount is going to stay the same. But there is work being done on the cars. And guys, I'm not being facetious here. Gravity does work on the cars to change its kinetic energy. So we're using potential energy as kind of a placeholder to remind us of how much work was done in getting the cars to the top of the hill. And we're saying that the cars have potential energy because they are above where they could fall to. They could fall all the way down to the ground here. We're saying that the amount of work done in lifting them stays with the car as a combination of potential energy and kinetic energy. And if there's nothing to take that energy away, the total energy in the system will stay the same all the time, no matter where the cars are in the track. But, and I mean this with complete sincerity, the best way to know if there's anything doing work on the system to take the energy away is to figure out how fast you think the object should be going and then actually build it and see how fast it's going when it gets there. You'll probably find that it's going slower there because something took energy away. Now, you wouldn't want to actually do that, right? If you're building it, you would prefer to kind of predict how much energy is being taken away. But for our sake, right now, we are just saying that we're dealing with the simplistic version of this. No friction, no air resistance, just to get past this. But obviously, no matter where we pick, any of these places in the track, gravity is always acting downwards. So when it comes to how gravity is affecting the car, it's always acting in the same direction. So no matter what the path is, only the component of the gravitational force downwards is ever changing the velocity of the car. And that's why it's path independent, because there's no part of the force that's in the direction of the track, unless the track were straight down. Go ahead.
In the equation, why do both masses on the right side cancel out when there's only one mass on the left?
So, I will demonstrate something I couldn't demonstrate earlier, and that's patience and alacrity. If I wish to use algebra to make my equations simpler, I know that one of the things I'm allowed to do is factor out a variable from every term in a polynomial. So I factored out the m from the term on the left, but there was only one term. I can factor out the m on both terms on the right because there are two terms in my polynomial. It's like the reverse of this distributive property. It's factoring. And now that I have factored it out, I can multiply both sides of an equation by anything I wish. So I will multiply both sides of the equation by 1 over m. And that will cancel out the m's here and cancel out the m's there. Does that make sense? I say this, and I know you asked the question, and I'm being a little facetious, but do you know how many times in this class I've watched you guys cancel out that and leave an m there? It's a lot. Worse are the times that there is no m here, there's like k here, and you cancel out these two m's. So your question is not unwarranted. I saw it on the last test. So it's not like it didn't happen just last week. It did. So now I'm trying to be very clear, like when I said to you at the beginning of class, there are just some things that are different in these years than in past. This is a mistake that is showing up more frequently for me. Do you understand? I need you to stop. Go ahead.
Why don't the gravities cancel out?
For the exact same reason. There's no g in this term. Past this stupid example, okay? So is there anybody else who wants to ask why the 1/2 doesn't go away? All right, so, wow, 600 equals 300 plus 1/2 v squared. I am done with this question because this is arithmetic, right? If you get the right answer, yay, I'm so proud of you, okay? But you understand that this is probably pretty small potatoes when it comes to what you have to do to find the velocity. Are we good? Because there's something else I have to explain that's more important than this. So if you're desperate, subtract 300, multiply by 2, get 600 again, take the square root. And I don't know what the square root of 600 is. Something around 70-something probably. 24. Not even close. There we go. So there, 24. So now we have the answers. 24 meters per second. What am I thinking? That's right. 25 squared is 625. All right. So with that being said, I want desperately to go on because what this really just means is, what do I do now? Repeat this 5 times? Find out how fast the car is going at the bottom here. Find out how fast the car is going some midway point on the track. Do you understand it becomes the same problem every single time? It's for you to practice, and you need that practice. But there should be more that we do here, because there's something else I want to have conveyed to you that I didn't convey. So we're not talking about our roller coaster any longer, but let's talk about just something simple like a car rolling down a hill. If we release the car and we know how high it is before we release it, we expect it to have a certain speed at the bottom. If it doesn't, then we know some of the energy was taken away. But it's not an arbitrary amount. We will know how much gravitational potential energy the object had here. And if we look at the amount of kinetic energy it has here, and these two aren't equal, if they're not equal, then whatever the difference is had to be work done by a non-conservative force. We either can add it to this side and say it went somewhere, or we could subtract it from this side and say it was taken away. Either way you want to think about it in your head is fine. But you have to be prepared for that eventuality.